Hello, everybody. This is Becca from Empowering Pumps and Equipment. Today, I have CFturbo here. We are going to be talking about part 2 of their next webinar on hydraulic design and multi-stage pumps. So I have Ralph Peter Mueller and Sasha Hanok with us. And so Ralph, Sasha, why don't you introduce yourselves?
Yeah, thanks, Becca. My name is Ralph Mueller. I'm co-founder of CFturbo and president of CFturbo Incorporated in Brooklyn.
Okay, thank you, Becca. So my name is Sasha Henoch. I'm a CFD engineer at CFturbo in Germany, and I'm working mainly on the optimization and design of pumps and fans.
Wonderful. Well, thank you both for being here. And, to give you guys a little recap, part 1 was all about basic modeling and CFD simulation. So we are going to have 2 more parts. So this part is going to be optimization in relation to diffusers. And then part 3 is going to be optimization related to impellers. So Sasha, why don't you take it away?
Thank you very much. So let me quickly share my screen. And I give you a welcome to our second part of our hydraulic design of multi-stage pumps. This one is about optimization. And in the last session, we showed you how to create an initial design of a multi-stage pump with CFturbo. We have performed 3D CFD simulations using ANSYS CFX and Sumerix MP. And we performed steady state and transient CFD analysis. As a result from our CFD studies, we found out that our impeller efficiency is around 92%, while the stage efficiency varies between 80 and 82%. Today's session, you can see the baseline design of our multi-stage pump we have created in CFturbo. Today's session is about the optimization of this multi-stage pump, and we have the following objectives. So at the beginning, we want to minimize the total pressure losses inside of the bowl diffusers, as you can see it right here, to improve the overall device efficiency. And additionally, we want to reduce the NPSHR by optimizing the impeller design of the first stage. Today, we will focus on the minimization of the total pressure losses inside of the bowl diffuser, and we leave the optimization of the NPSH for a separate session that will be coming next year. So let's talk a little bit about our workflow setup. We created workflows with CFturbo inside of ANSYS Workbench. Of course, the geometry modeling was done with CFturbo. For the mesh creation, we have relied on TurboGrid. We used ANSYS CFX as a CFD solver, and we used Optislang for a sensitivity analysis of our geometry parameters, and we also used Optislang for the optimization process of the bowl diffuser design. Okay, let's talk about the CFturbo model. And a very important issue on optimization is to keep the computational costs low, because we will create multiple designs, hundreds of designs, and that's for this reason we cannot rely on computational heavy models. So that's why we try to keep the computational costs low and reduce the CFturbo model to a single stage pump. And we also added artificial extensions to the model for numerical reasons. We wanted to reduce the computational costs for the CFD analysis further. So that's why we used single plate passages from TurboGrid for the CFD setup. And the domain coupling between the rotor and the stator domain was performed by using a mixing plane approach. So after we have run initial simulations of our baseline design, you can see now a streamline plot right here. And we are coming from the left-hand side of the picture. And you can see the streamlines nicely attached to the flow passage inside of the impeller. And it also nicely attaches at the beginning of the diffuser inside of the bowl diffuser. But if we take a look at the back of our bowl diffuser, you can see that we are starting to get flow separation inside of the plate channel, and also this flow separation will be transported in the downstream located regions. If we take a look at our plate-to-plate view, in this case, you will see the midspan as a plot configuration. You can see the impeller domain right here, and located downstream, you will see the domain of the bowl diffuser. And as you can already guess, we see large flow separations inside of the plate passage of the bowl diffuser. So what we have done is we go back into CFturbo, we activate certain geometry parameters, and we are using these parameters to perform different studies and optimization to gain a better bowl diffuser design. So what we have done is, you can see right now the meridional contour design step inside of CFturbo. We keep the actual extent of the bowl diffuser constant, as you can see it right here. Also, the inlet and outlet dimension of the bowl diffuser is fixed. But for example, we allow the meridional contour of the bowl diffuser to be changed, and therefore we have access to certain parameters that define the hub shroud contour, as you can see it in the picture on the right-hand side. Additionally, we have geometry parameters for the meridional plate position. So we are able to change the position of the leading edge in the meridional contour, as well as the position of the trailing edge. So this gives us in total 14 geometry parameters for the meridional design of the bowl diffuser. And in the next step, we will talk about the plate properties of our bowl diffuser. So mainly, we are going to change the plate angles, which are defined by 4 geometry parameters, 2 parameters for the leading edge and 2 parameters for the trailing edge. And additionally, we activated the number of plates as a parameter that is allowed to change. But in this case, we defined a discrete set of number of plates to avoid unfavorable impeller-stator interferences. So for the plate properties, this gives us 5 geometry parameters for the definition of the bowl diffuser plate. In the next design step, I will talk about the mean-line design of our bowl diffuser. We activated the geometry parameter that changed the circumferential position of the leading edge, which is defined by 2 parameters, as you can see it right here. So basically what you are seeing is the meridional coordinate of the plates versus the tangential coordinate. And additionally, we allowed the plate wrap angle, which is defined by 2 parameters, to be changed in the optimization process. And in total, this gives us 4 geometry parameters for the bowl diffuser mean-line design. So all in all, we have 23 geometry parameters from CFturbo that are allowed to change to create a new bowl diffuser design that is hopefully more efficient than the baseline design. From the CFD analysis, we get 7 responses. So of course, an important parameter is the total pressure difference of the impeller and of the pump stage, but also the internal efficiency of the impeller and as well as the stage shaft power of the impeller. And what was very important to us was the static pressure at the bowl diffuser outlet, as well as the total pressure drop inside of the bowl diffuser. So then we ran an DOE, a design of experiments, and let's give you a little bit about the statistics. So we have created 300 samples via a Latin hypercube sampling. And to give you a feeling for that, 20% of the designs failed in TurboGrid due to non-valid meshes or meshes with negative volume cells. 10 designs failed in CFturbo, mainly because of extrapolation errors, and 3% of the designs failed inside of CFX. And that's the most heavy part, because you already meshed the geometry and started already the simulation. So after the DOE, we get some sort of correlation matrix with anthill plots. And in this correlation matrix, we will see the correlation between our parameters we have activated and our responses we get from the CFD analysis. And we also see so-called anthill plots, which is just scatter plots, where we can see every data point that was created with every design. The most relevant responses for our imminent optimization was the static pressure at our bowl diffuser outlet, as well as the total pressure drop inside of the bowl diffuser. And if we plot the results from our DOE using these two responses, you can see that we are getting some sort of clustered data. You can see that the y-axis is the total pressure drop inside of the bowl diffuser. The x-axis is the outlet static pressure. And in green, you can see the performance of our baseline design. And the black markers are the designs from the DOE. So basically, we want to achieve an optimal design that fits inside of this target area where we're going to minimize our total pressure drop inside of the bowl diffuser. And of course, the region where we have a high static pressure at the bowl diffuser outlet, as the circumferential velocity inside of the bowl diffuser is reduced. And as I said, we want to reduce the total pressure losses inside of the bowl diffuser. So mainly we target this area that is displayed in this chart. From the DOE, we also get statistical post-processing features. So for example, for the static pressure at the bowl diffuser outlet, we are able to display our correlation coefficients to see which geometry parameter has the most influence on our response. So, and we performed this for the static pressure at the bowl diffuser outlet, as well as the total pressure drop inside of this bowl diffusers. And based on this analysis, we used this information as some initial guess what parameters needed to be activated for the upcoming optimization run. So basically, for the optimization, we have used an evolutionary algorithm and used the results from our DOE as initial population. Based on the sensitivity analysis, we were able to reduce our set of parameters from 23 parameters down to 10. And of course, since this is an optimization, we need to define an objective. In this case, it's a single objective for our optimization problem. And we want to maximize the static pressure at the bowl diffuser outlet, because by that, we make sure that we are reducing the internal pressure losses inside of the bowl diffuser. And additionally, we are reducing the flow swirl at the outlet of our bowl diffuser. Also, we had no additional constraints for our design, so this makes it really easy for our optimization run. So let's talk about the optimization statistics. Again, we have created 300 designs, of which 4% failed. And if we take a look at our response history, so as our evolutionary algorithm develops or progresses, you can see that our response history for the static pressure at the bowl diffuser outlet is maximized, and at some point the evolutionary algorithm starts to converge to a more constant limit, so the algorithm is not able to improve the design by much. So you can see the change at the beginning is pretty high, and as the response history progresses, the improvements get smaller and smaller, and in the end, the evolutionary algorithm returns the best solution. So again, this is the chart I have also displayed earlier. We see the total pressure drop inside of the bowl diffuser over the outlet static pressure of the bowl diffuser. In black again are marked the designs from the DOE. In green we can see our baseline design, And then in red, we can see the results from the optimization run. And as you can already see, so most of the designs that were created by the optimization algorithm already perform better than our baseline design. So only 3 designs were created that are performing worse. And let's zoom in on this area where all the data seems to be clustered. Yeah, you can see if you take a look at our baseline design and maybe the best design from our DOE is that yeah, the best design from the sensitivity analysis already shows a great improvement compared to the baseline design. And if we consider additionally the best design from our optimization run, you can see that the improvement from the best DOE result is only small. So basically we had already a pretty good design coming from the DOE, but of course that there's no guarantee that you will achieve such good results purely from a DOE without an optimization. Okay, so let's talk about the results from our optimization. So basically, if we take a look at the head of our impeller, we see no changes compared to the baseline design. This is reasonable because we did not modify our impeller. But if we take a look at the head development inside of our stage, you can see that compared to our baseline design, we have gained 4% when it comes to the head of our pump stage. If we take a look at our efficiency, we can see similar results. So for the impeller efficiency, we see no difference at all, which is reasonable. But if we compare the efficiency from the pump stage, you can see that we were able to increase the efficiency by 4 percentage points. If we take a look at our responses coming from the bowl diffuser, you can see that we were able to decrease the total pressure drop inside of the bowl diffuser by 42%. So mainly from a total pressure drop of 6,800 Pascal down to something around 3,800. And if we take a look at our static pressure at the bowl diffuser outlet, we were able to increase the static pressure by roughly 4% with the optimization run. If we take a closer look at the CFD results, again, you will see the plate-to-plate view for our baseline design. And as I have shown earlier, we see large flow separations inside of the plate channel of the bowl diffuser. And if we compare it to the best design from our optimization, you can see that we were able to drastically reduce these areas of flow separation, as you can see it right here. So basically, we will see a more efficient design when it comes to to the flow quantities we post-process from the CFD results. And also, if we take a look at our 3D view, so again, this is our baseline design I have showed you earlier in the presentation, and we were seeing flow separations close to the bowl diffuser outlet, where this turbulent flow quantities were transported in the areas downstream. And if we show how the best design from the optimization perform, it's really hard. We cannot spot any flow separation at all. So the flow stays attached to the plate, and the upstream located, the downstream located component sees a much more uniform flow field. So let's compare the two different designs. So in green, you can see the baseline design, which we have created in the last session. And in orange, you can see the best design from our optimization run. So compared to our baseline design, we have increased the number of plates from 8 to 10. We have a higher plate lean angle at the trailing edge for our optimized result, which can be seen right here. So compared to our baseline design in green, You can see at the trailing edge that the plate lean angle is much higher. And if we take a look at the meridional contour design, you can see that our optimized result in orange provides a much smoother flow redirection in meridional flow view. So based on this optimized design, we have ran, again, transient CFD results for our baseline design. In this case, we simulated the whole multi-stage pump as a 360-degree model using Zimerix as our CFD solver. And if we take a look at our velocity magnitude on our bowl diffuser outlet right here, this cross section, you can see that we have a flow field that's not very uniform. So we have areas with high velocity at low radius areas, and we have areas with a very low velocity magnitude, which are located at the shroud of the bowl diffuser. And if we are going to show you the results from our best design optimization, you can already see that in this area, we have a much more uniform flow field compared to our baseline design, where you can see these areas with a low velocity magnitude show that some sort of flow separation occurs. And if we are going to use the same cross section, you can see that compared to our initial design, we achieve a much more uniform flow field at the bowl diffuser outlet, mainly because we reduce this area with a high velocity magnitude. And let's talk about the overall results from our transient CFD runs. So compared to our baseline, we were able to increase the pump head for every stage, as you can see it right here. The most gains are visible for the first pump stage, but we also see smaller gains for pump stage number 2 and pump stage number 3. When it comes to the stage efficiency, we can see large increases for every pump stage. So we achieve an overall better design with this bowl diffuser modification. And if we take a look at the shaft power, you can see that for the first pump stage, we have nearly identical values when it comes to the shaft power, but we see small decreases in the shaft power for pump stage number 2 and number 3, mainly because we were able to improve the flow field and its uniformity for the second and third impeller, mainly the impeller inlet. And if we take a look at the overall flow quantities, you can see for the 360-degree multi-stage pump, the transient results show an overall head increase of roughly 2%. We were able to improve the overall efficiency of our multi-stage pump by 2.5 percentage points. And we were able to lower the overall shaft power of our multi-stage pump accordingly. So all in all, the transient CFD results of our multi-stage pump show a higher head for the optimized design, while the overall shaft power is lowered. So, and in the next step, we would like to perform a multi-objective optimization of our first stage for an improved NPSH. And as you can see, which is displayed in the image, we can see isosurfaces at our first impeller, and in blue are areas which are prone to cavitation. And we want to improve this design. And this is what we are going to show you in the next session, which would be part 3, hydraulic design of our multi-stage pump, which will be available in February 2022. So that's all from my side from today. So thank you very much. And yeah, I'm open for questions.
All right, Sasha, you can go ahead and stop sharing your screen. And let's bring us all back on here. There we go. So Sasha, thank you so much for your presentation. Listening to you and Ralph, any of the things that you guys are able to accomplish with using your simulations and design is just mind-blowing to me. I'm also not an engineer, so that's probably part of it. But if you would indulge me just a little bit, would you be able to go into, just why is it so important to eliminate this flow separation?
Well, so basically, flow separation always means that we have some sort of losses. And losses is equivalent to a lower overall efficiency, and lower overall efficiency means that our costs to run the pump increase as the shaft power, for example, also increases, or we have to use larger pumps to counteract on the lower efficiency, and larger pumps means also higher costs.
Gotcha, which nobody wants.
Of course.
Awesome. Well, Ralph, why don't you, talk a little bit about why you think optimization as a whole is so important?
Yeah, well, a general thing is these kind of work, what Sasha here presented and what we are doing in our daily life. So this is or has been more or less an intuitive job in the past, right? So that means you needed expert engineers which had a lot of decades of experience, let's say, to changing geometries to come up with good results. So right, but currently there's a new generation of engineers which maybe comes not to the world, but with other, let's say, tools in hand. And so for us, it's also a possibility, I would say, that we can make optimization. As I would say, even now, it has become affordable, right? So in the past, so it is a matter of experts, but now also the young engineers are able to run optimization jobs for pumps, and this is really exciting, I would say.
That is exciting, especially, knowing that they can start at that level, like as they come in and learn how to do this, versus something that maybe back in the day was like the peak of their, career. So that it's more options and just more expertise that they're able to do, even at that introductory kind of stage.
Yeah, I would say it's still important that someone who make hydraulic pump design understands what the pump does and how, let's say, a pressure field should look like. So this is clear. So this should never be a black box, in our opinion. On the other hand, but you get tools which gives you so much more capabilities in doing it faster, getting more good results in a shorter period of time. I think this is the exciting thing, and this is by combining the right software tools.
Absolutely. And so, Sasha, you had mentioned it just a little bit there at the end, but can you tell everybody, maybe what you're most excited about to talk in part 3 around impeller optimization?
Well, so basically, as I already said, the next step is the optimization of the first impeller stage. And this will be a multi-objective optimization problem. That means we need to focus on more than one response we get from our CFD analysis. In this case, we want to lower the NPSH-R, but we will see some kind of trade-off when it comes to impeller efficiency. So basically, what's the interesting part is probably we will get to a point where we cannot improve the NPSH without lowering our impeller efficiency, and there we will see some sort of Pareto front, and that's very interesting when it comes to design choices, because as Ralph said, in the past, getting a good design was a result of the engineer's intuition and the engineer's knowledge. And part of this can be replaced with some sort of optimization algorithms. But the final design choice, and I think this is a more realistic way, you will never get the most optimal design. You will always have some trade-off, and that is what we will see in the next session, where we are performing multi-phase CFD analysis, multi-objective optimization runs, and this is, I think, a more realistic approach when it comes to getting the final design of a pump or improve the designs at all.
Awesome. Well, I'm very much looking forward to part 3, and I hope you all enjoyed part 2. And, you know, Sasha, Ralph, thank you so much for your time. And yeah, to be continued.
Okay, thank you. Thank you, Becca.
Thank you.
Bye.